ado, I'm going to introduce our speaker tonight, Mr. Mike Adler, Dr. Mike Adler, who is, amongst many things, also a member of the geologists at Jackson Hole, and someone who has contributed to present us some really wonderful presentations over the past, I don't know, 5 or so years.
Probably longer than that.
Us. Yeah. And tonight, I think will be no exception. Mike graduated with a PhD
you better start this.
in solid-state physics, MIT in 1971. He had nearly a 30-year career with General Electric until he did what we all eventually do, which is not necessarily stop working, just stop being paid. In 2000, he's widely published in the area of semiconductor physics, over 100 papers. He's long a fellow of the IEEE, Institute of Electrical and Electronics Engineers, and he was president of that during the year 2003. So the things that he doesn't get paid for, at least not much, are hobbies of astronomy, photography, certainly traveling with Virginia, who is right here, his lovely wife. And as he has said multiple times, he does 2 trips of a lifetime each year, which is not too bad of a gig to have. And while the photos that you're seeing tonight, unless I'm terribly mistaken, none will have been taken from Mike's his observatory down at their house. You have seen, you've been through the library here, you've seen several of the displays that he had in the lobby out here. He did have, actually the first display that was in the library out here, that would have been, it says 2012, it would have been 2013. And then he had a more recent one in 2017, and his astrophotography is just astonishing. So, I think without further ado, I've probably rambled on too long already. I'm going to ask you to join me in welcoming Mike Adler. If you would, if you have one of these that's not turned on, please do so.
Yeah, speaking of. Yeah.
Mike's going to turn off it.
Yeah, you're reminding me. Okay. Turn off the volume at the ringer anyway. Okay, John, thank you very much. Now, if I can get my phone to shut off, I'll be in good shape.
That's going to be the most exciting part of the talk.
Okay, got it. All right, it's off. At least the ringer's off. Okay, so this is really part 2 of what is now becoming a 3-part series. Last January, I talked about Pluto and Mars, and tonight is going to be about Jupiter and Saturn. And the 2 largest the 2 largest planets and the 2 largest gas giants in our solar system. So, so the sources for the talk are 163 images from the Juno mission, which is the current mission that's flying in around Jupiter, and then all 3,363 images from the Cassini mission, which can be found on these photojournals. And I must say, I looked at every one of them to try to pick the best ones out. And so there's a fair amount of research that went into this talk. Anyway, there's information from NASA, many NASA sites, from the Astronomy and Sky and Telescope magazines, numerous recent papers. What's pretty interesting, I'll try to remember to mention it, but there's papers just this last year, within the last 2 years, about both Jupiter and, which are breaking new ground, just like on Mars and Pluto. And there are some graphics in here from Astronomy Today. And also, I must say that even though you're not going to see them here, you'll probably notice that there's a lot of footnotes in the talk on these view graphs. And so if you want to read more about any of this, other than any questions you want to give me afterwards, you can download it. I'll make sure it's up and available for you so you can download it. Okay, so the talk outline is we're going to start with Jupiter, and then we're going to move to Saturn, and it's kind of going to be the same flow, but there's a little more information on some topics for one planet than the other. Okay, so we're going to first talk about how does the solar system form very, very briefly, but basically the solar system formed at the same time the sun was formed, about 4.5 billion years ago. And the solar system is the leftover junk from that didn't get coalesced into the sun. And each of the planets are coalesced from the stuff that was present roughly where they currently are. So the terrestrial planets are made, like Earth and Venus and Mars, are made out of solid stuff, because that was the stuff that would remain close to the heat of the sun. And the planets, starting with Jupiter, are all the gas giants. They're made up of frozen gases. So, and so we're going to talk about the two gas giants. I should just mention, you can try to read some of this stuff, but I'm probably going to blow through it. This was for me as I put these things together. And there was a lot of research to somehow get all the information. So I felt like I needed to write it down. But I'm not going to hit all these bullets, so don't worry about that. I'm just going to hit them episodically. These are some simple cartoons of the gas giants. Jupiter, it gives you at least some idea what the relative sizes are, and there's Earth up there. These are way oversimplified, but the basic ingredients is that the outer layers are all gas, and then they become liquid as you get closer in, and they may or may not actually have a solid core, and we'll be talking about some of that. So talking about Jupiter first, Jupiter is about, I won't get into the miles, but it's 5.2 times the distance from the Earth to the Sun. That's where Jupiter is, so it's out there. It completes its orbit just under 12 years, that is orbit around the Sun. What's also impressive about Jupiter is it has a 10-hour orbital period, a day. So the day, it just whips around extremely fast. And there's actually a resonance between Jupiter and Saturn. That means their orbital periods have some relationship to them. They're tied together. The axis of Jupiter is almost non-existent, so there's very little seasonal changes. The clouds, at the top of the clouds, it's it's nice and warm at minus 234 F. But the core temperatures is just a little warmer. 43,000 degrees Fahrenheit. So, yeah. Anyway, so that's it. And you'll all know that Jupiter has all of these interesting bands, and we'll talk about those in the Great Red Spot. What's unusual, I'm going to now talk about the Juno expedition or mission, which is the mission that just is now flying above Jupiter. It's the second orbital mission in Jupiter. Galileo was the first. But Juno is giving us a view that's very different from the Galileo view, and that is going right over the poles. And so this is a view of the south pole of Jupiter. And as you may or may not know, we'll talk about it, but the winds on Jupiter are pretty extraordinary. They're like 380 miles an hour. This is the satellite, the Juno satellite. It's one of the first satellites that's actually powered by the sun. So these are huge solar panels, pretty high. Each one of them is 9 meters, almost 30 feet. And it's got a core. And it was launched in 2011, and it made a few spins around the near Earth area, and it entered orbit in July 5th of 2016. And it has lots of instruments on it. It has a gravity space instrument to measure gravity and magnetic field. It has a microwave radiometer, so it can actually peer inside the clouds for the first satellite to be able to do that. It can measure electric fields, I mentioned magnetic fields, plasma waves, particles. It has cameras that take pictures in the UV and in the infrared, and it has a visual image camera as well. So it's really loaded with stuff. This is the interesting, now these are the orbits. So the mission is quite different from the previous missions. That is, it changes its location around the planet. There's 33 of these that are planned. Juno does a 53-day orbit around, and so it goes way out and then swings back in to a slightly different location, then another and another and another. It was originally going to be 14 hours. There were some problems with the engines, and so they extended it. They left it at 53 hours rather than risking having the thing malfunction. So it's going to take them about 4.5 years to complete this mission. So it's just really just starting. So this is Jupiter's atmosphere. It's been measured down to about 150 kilometers below the surface. Now, how do you define the surface in a planet that doesn't have a surface? Well, they arbitrarily define a surface at pressure of 1 bar, in other words, 1 Earth atmosphere. And so that's considered the reference for most of the gas planets is 1 bar. And the top of the atmosphere is made up of clouds of some water, ammonium hydrosulfide, ammonium ice, and haze layers, and all sorts of stuff. And then it transitions gradually into molecular hydrogen and then eventually into metallic hydrogen, where you have electrons and protons. Yeah, in fact, below 10,000 kilometers, you have what's called metallic hydrogen. So there's no clear boundary between the gases on the surface and the liquid. It gradually becomes that, and there's some phase changes that go on. Yeah, in fact, at above 12 atmospheres, hydrogen becomes a critical fluid, a superfluid, and it loses this distinction between gas and liquid. Okay, so this is the same picture that I had at the beginning. This is Juno's picture, and if you've seen other pictures of Jupiter, you'll just marvel in the detail in this. This is just incredible. Now, you also know there's this big red spot, and there's a white spot here. There's also all these bands, and these bands are produced by the Coriolis force, the same force that causes the atmosphere on the Earth, the northern atmosphere, to go from west to east, and the atmosphere below the equator east to west. Well, this is the same thing. The difference is that Jupiter doesn't have a surface. It's a gas and a liquid, and so you get many more bands are created here rather than just, say, a single one. And the planet is mostly hydrogen with some helium. And these various bands have broad names. The lighter areas are called zones, and the darker areas are called belts. And the zones represent areas of upwelling of the atmosphere, and the belts the atmosphere is dropping down. And the ammonium concentration actually changes the color. So I think the denser ones, there's ammonia at higher altitudes that make them look darker. Yeah, this image, for your information, was just taken this April from a distance of about, well, it varies, you see. It varies from 11,000 to 42,000 miles because the satellite is moving. So these are composite images that are taken, and they assemble them into a single image.
Why is the red spot red?
Oh, good question. No one knows for sure, but they think it's ammonium sulfide that's been welled up from the inside. But that's not 100% known, but it's some gas. The red spot goes in quite a ways, and we'll talk about these things, but it's thinking it's definitely some trace elements that have squirted up from the red spot is not here forever, by the way, and we'll talk about that too. Okay, so these are the winds, and they whip right along. And this is kilometers per hour. I may have screwed up my units earlier. It's about 350 kilometers, not miles per hour. This is, let's see, I'm going to need to get over to the computer to do this. This actually is an image taken by Voyager 1 in 1979. Isn't that amazing? Let's see if this is going to work. Ooh, I guess maybe not. Well, okay, best laid plans. Oh, well. Okay, what it does, which it's not doing, and I'm not going to dwell on it, It's kind of a neat video, though. It's not. It's a bunch of stills, is what it is. But what it shows is the bands. The lighter colored zones go prograde. They go west to east, and the darker bands go east to west. And the red spot circles counterclockwise, and all of that is in motion. If I could got this thing to work, which I can't. So too bad. All right. On Jupiter, there are hundreds of vortices, and here's a bunch of them, again, in another Juno image. Isn't that an amazing photograph? These are circular rotating structures. They're either cyclones or anticyclones, meaning they either rotate clockwise or anticlockwise. 90% of the vortices, larger than about 1,000 miles in size, are clockwise, or anti-clockwise, excuse me. And the Great Red Spot and another large one called Oval BA, which just formed 10 years ago, are counterclockwise. So the biggest ones rotate counterclockwise. Yeah, and you know, Brent's question was, structures are red, arguably due to dredging up a red material from the planet's depths. That's the answer. What that red material is exactly, no one knows quite sure. So this is a closer up image, again taken by Juno Cam 4, 1 of 18. Yeah, and yeah, this doesn't show the number. Each one of these pictures has a number to it, and if you go into the references, which is below every slide, it tells you what number is. You can go online and look up that, and you can see the picture yourself. Plus, it gives you a description of some of what it is. It rotates, the Great White Spot rotates counterclockwise about 250 miles an hour. It has an orbit, time to go around, about 6 Earth days. It's big, so it takes a while, even though it's whipping around. It's a little over 1.3 sizes of the Earth. It once was twice that size, and it's shrinking fast. So in another 20 years, it might not exist. So it's just great. These things don't last forever. The estimate is 300 years overall. It produces a fair amount of heat, which has been measured. Yeah. Yeah, I have the dimensions here, but the important thing is that Earth is like this to this in size. Okay, so talking about the layers in a little more detail. So here they are. The topmost layer is the outer atmosphere, which is that graphic we showed a little bit ago. There's something called the deep atmosphere, which extends about 300 kilometers below. Then you get into the hydrogen layers, which are first weakly conducting and then highly conductive. It's still considered molecular hydrogen, in other words, H2, but there's some of these hydrogen molecules which have broken apart and into proton, electron, and they become what's called highly conducting. And then we'll get into the lower levels. The bulk of the mantle is called the metallic mantle. It is electrically conducting hydrogen. Now, the hydrogen is broken up into electrons and protons, and so it's highly conducting. And the bulk of the planet is this metallic liquid hydrogen. There are clouds of helium, and then the middle part are the denser elements. The one cartoon I showed earlier suggested, and here's the Earth's radius, by the way, suggested that the center might be rocky, but it's no longer thought that way. It's now thinking it's not solid, and I'll talk a little bit more about that. In fact, helium actually dissolves and comes down as rain in here. Okay, and so one of the big changes from the Juno mission to compared to the Galileo mission, which ended around over 10 years ago, is that there's a microwave radiometer, an MDR instrument, which actually looks down. So this shows that various wavelengths and the depths that the microwave actually goes below the surface. And you can see these are pressure, and this is distance over here. And what they've determined is they thought that these layers would be fairly uniform as you went down, but they are not. And this orange area here is ammonia, and it has a spike just about here. And the ammonia is thought to have a similar role as to water in terms of the weather on Jupiter. In fact, they think of the ammonia as like a Hadley cell near the Earth's equator. What the Hadley cell does is water moisture rises up and then comes down about 30 degrees north or south. And that's kind of what's going on here with the ammonia. So it's somewhat similar, except that it's ammonia instead of water. This is a more detailed picture. This is actually in a very recent science article that just came out earlier this year, and it's just showing you the details. This is the upper, very top layer of the atmosphere, and then as you're going down 400 kilometers, you get into a solid area, not solid, but more or less uniform, but then at the equator there's this huge plume that goes up. Okay, so that's kind of that's all I'm going to talk about, the upper atmosphere, except for the polar region. So this is a picture of the south polar region, and it's really different. This is Juno is the first satellite where giving us a really good look at this, because what you do is you go from these nice bands that we've been looking at, you see in all the pictures, to this pattern on top, and these are storms. These are a mix of vortexes, small vortexes. Actually, on the south, I think there's 5 of them, and you'll see it clearer in a bit. And there's a similar view of the north, which I'll show you in a bit too. Okay, so this is a picture of the North Polar region using the IR instrument, and this is able to look down 30 miles below the surface. These, you could clearly see these 1, 2, 3, 4, 5, 6, 7, 8 vortices with a central vortex as well. And these things are about 2,500 to 3,000 miles in size. The yellow area is warm by standards of Jupiter. It's 9 degrees Fahrenheit. The reddish area is minus 181 degrees Fahrenheit, much cooler. So there's several, and this is again out of a very recent scientific paper that compares the visual. This is the North Pole. Notice the north is only 5. 1, 2, 3, 4, 5. The south is 8. This is the visual image of part of this. There's the center. That's the pole. There's the pole, and you can see some of these what they look like in visual light versus IR. And this is the South Pole, and it's the same thing. This was taken on the 4th pass of the satellite going around on February of 2017. This is a visual picture now of these vortexes on the North Pole. The velocities here are pretty fast, on the order of, on the average, say 250 kilometers an hour, and they have a period of about 30 to 60 hours. What's also amazing about this is Juno goes by here every 53 days, and they don't see much change, which is remarkable. And so this is a question. Why don't you see any change? There's a central vortex that's just ripping around, so it seems like there's a lot of mixing going on, but these 8 on the north and 5 on the south don't change very much. And so that's, and why don't they merge? They seem to stay there. They don't change much over those over subsequent images.
You keep saying 8 and 5, but the pictures seem to show 8 on both poles.
No, they're not. You see, here they are. Here's the north. 1, 2, 3, 4, 5.
You're skipping some.
1, 2, 3, 4. Well, it looks like 6. They say 5. Maybe the bottom has 8 though. 1, 2, 3, 4, 5. Anyway. Okay, moving on. The answer is 8 and 5. I guess some of those things are not considered vortex. Anyway. Okay, lightning. Lightning has been observed on Jupiter back into the days of Voyager 1 in 1979. And it wasn't clear what it was due to. and it's unusual that it only occurs in the northern hemisphere and not in the temperate belts, if you want to call that, around the equator. Earth is just the opposite. And so one of the questions is why? Well, Earth receives about 25 times the sunlight that Jupiter does. And the analysis suggests that sunlight actually stabilizes the atmosphere low down, and it doesn't really reach the poles, and so it leaves the natural instability in those vortexes there. And then on top of that, there's a bunch of charged particles that are spit out by one of the moons. We'll talk about that, Io, and that combination results in thunderstorms of ammonia and lightning. So anyway, this is again another technical paper that's come out not too long ago. Now, one of the other goals of Juno was to measure the gravity of, because this has never been done before either, this is some of the data, and this shows the non-uniformity in the gravity, it's quite non-uniform, and this is just. This is the wind gradient. This is the actual. This is the wind gradient we showed you earlier, and this is the gravity. And so there's definitely a relationship between the wind and the gravity. But the gravity is very asymmetrical on the planet, and the way it's measured is that they're actually measuring Doppler shifts in the microwave emission and an X and K band on the spacecraft going back, picked up on Earth, and by correlating the change in speed, they're inferring the change in the gravity. And so there's lots of atmospheric and internal flows going on. And that's resulting in, that's connected to the circulation on the planet quite clearly. And one of the questions is, how deep do these bands go? And by analyzing the gravity asymmetry that I just showed you, there have been papers that just came out in March 8th of 2018. There's actually 4 papers in Nature, which I dutifully read, by the way, to prepare this talk for you folks. And this is what comes out. This is actually the change in the gravity, or actually the circulation, I should say, based on the gravity measurements. It's an analysis, but it shows that it actually goes down 4,000 kilometers from the surface. This is new data, just analyzed, and this is the location of the inflection point. This place where it bends over, right, kind of like in the middle, as a function of latitude. So it's clearly the deepest at the equator, 0 of latitude, and then it drops, and it comes the speed drops off as you go up, and you can see the wind speed of the surface measurements bear that out. And I won't go into this bottom, but it's just a comparison of the variation in gravity with latitude, both experiment and measurement. This is another paper that appeared in that same issue, and what this does is shows a probability graph, and that's what this is, of where there's likely to be, where the depth of wind is, where the wind stops. And it comes out pretty much around 3,000 plus of kilometers. But on this side of it, there's lots of wind, or it changes and gets very high at the surface. Beyond that, it almost stops. And the reason it stops is that the conductivity gets bigger. You have metallic hydrogen, and you have this huge magnetic field. And the net result is that the drag caused by the conductivity of the magnetic field are large enough to stop those fluid motions. So it's all tied in. So the winds, this penetration, the change in gravity with depth, and the winds, it's all tied together. Saturn has a 10 times weaker magnetic field than Jupiter, and as a result of that, this depth profile is going to move much deeper because the magnetic field won't get strong enough to freeze this motion of the hydrogen, metallic hydrogen, until you get to higher gravity. And also Saturn has lower gravity too. So next topic is the magnetosphere. Jupiter has a huge magnetosphere, and it comes from motion associated with the metallic or the highly conducting layers. So there's motion in that highly conducted layer that's whipping around, and that's creating a magnetic field. So it's not in the core like in Earth. It's the liquid iron nickel core in Earth that's moving, but on Saturn it's not at the it's in this upper area, either in the highly in this molecular hydrogen area or in the area that is the metallic hydrogen. And in fact, but anyway, so that's what creates it. It's called a dynamo, and it's the motion of this that's creating this magnetic field. It's huge compared. The dipole field is 20,000 times greater than on Earth, and the surface fields are 20 times greater. So these are huge magnetic fields. And it's also interesting that we'll talk about Io, which is one of the Galilean satellites, the closest one in. It is volcanic, and it spews lots of volcanic material into the atmosphere around, or into the area around Jupiter, and has created a plasma torus that's is a part of and it's spit out a lot of it's also responsible for the aurora, which I'll show you in a bit. But it's quite a story. This is a measurement that has been done of the magnetic field, and this is, if you look at it here, each one of these is, I guess, 30 degrees apart, and this is up and down. So this is north to south, east to west, and it's on a flat, all stretched out on a flat plate. You'll see it's extremely non-uniform. Just like the gravity is non-uniform, so is the magnetic field. So the red area, as you can see, is up there around 60 Gauss, and the blue area is down here, much less smaller. This is what it looks like from the top and the bottom, the north and the south poles.
So like you're telling me, if I scale the Earth's magnetic field up to the size of Jupiter, this is way bigger than that.
Yeah, yeah. Yeah, this dynamo is because of everything, you know, we talked about, the fast rotation of the planet, these motions of these the atmosphere, but also presumably the motion of the hydrogen atoms are just very fast and are creating this very high field. And it's much closer to the surface. It's right there. It's way above, so it's not at the center. This is, so one of the effects of a magnetic field is aurora. Now the difference is with Earth. Earth's aurora occurs because particles from the sun, solar wind, interact with the magnetic field, charged particles, and you get the emission from the Earth's atmosphere is excited by the solar winds and ionizes them, and then they emit the light. On Jupiter, it's very different. It's the ionization is being occurred. It's not the solar wind that's doing it. It's the charged particles from the volcanoes from Io that are creating. And this is the North Pole aurora, and it's a permanent aurora. It's not like it's always there because Io is continuously spitting out these particles. And this is the South Pole. The yellow track is the track that Juno takes. So it's quite a circular track as it's going around here. And this is the UV intensity, ultraviolet intensity, and this is the absorption of this light by methane. And this is for the South Pole, and this is the North Pole. Yeah, oh yeah, and this is a graph, not a graph, it's a picture by the Hubble of the aurora taken by Hubble on the North Pole. So pretty cool. And again, it's a permanent aurora. Okay, so we're going to move on to Jupiter's moons, and I'm only going to talk about in detail the Galilean moons, these four. There are 79 moons orbiting Jupiter, the most of any of the of any of the planets. There are 8 that are called regular, so there's, which means that they orbit in the same direction as Jupiter is rotating, and they have nearly circular orbits, and they're on the plane of Jupiter's rotation. The remainder are irregular with both prograde and retrograde, and they have way weird inclinations and eccentricities. So we're going to talk about these 4. Most of the mass in all of those 79 are in these 4, by the way, all but something like 99.997% of the total mass in orbit around Jupiter is with these 4 Galilean, and the biggest one being Ganymede. This is the pattern of the irregular moons. They're all over the place. They're all over the place. That's Jupiter's spin. That's the its spin axis, and these things are everywhere. The regular ones are pretty much lined up with the just like on, yeah. So this is Io. This is not Juno hasn't taken really good pictures of these satellites. It's concentrated on Jupiter itself. This was taken by Galileo on July 3rd of 1999. It's a false color picture to illustrate, but there's something like, it has a period of about 2 days, Earth days, a surface temperature of about -261, has 100 mountains higher than 6,000 meters. It's composed of silica rock and either a sulfide or iron core, and it's this makes it close to the terrestrial planets in its overall in its makeup, and it has definitely it's the most active of any of the planets volcanically. It also, because of the fact that Io is very close to Jupiter, and Jupiter has this huge gravity field, the surface, now this is not an ocean, this is the surface of the planet, moves as much as 300 feet up and down because of the tidal effects associated with Jupiter itself. So that's pretty amazing. And it also has, the magnetic fields are also turning Io into an electric generator, and it's responsible for, it plays a key role in generating the lightning that we talked about, because it's also throwing up the charged particles, and so it's creating the aurora as well. Also, as Jupiter rotates, the magnetic field strips off about 1 ton of Io's atmosphere every second. So all that stuff is populating the area around the planet and contributing to the aurora, contributing to the magnetosphere around. And this is just zoomed in on one of the volcanoes. There are many of them. This vent is 19 miles across, and this stuff is about 155 miles. And the color is due to various compounds of sulfur and others. Okay, moving on to Europa. It also has a fairly fast orbit, 3.5 days. Galileo made many passes over it. Its surface is covered with ice, and these cracks are thought to be due to, again, tidal effects, the stretching and compression of the surface of the planet due to the magnetic field, due to the gravity fields of Jupiter. The lack of, you'll notice there are very few, in fact you can't see any from this picture, any craters, so it's also thought to be fairly young geologically, meaning 60 to 90 million years. This is a more detailed picture of it. But interestingly enough, based on the fact that the surface is ice, it's thought that there is underneath this icy surface, there is an ocean of salt water. And this was determined a couple of ways, but the bottom line is it looks like it's underneath about 10 to 15 miles of ice, and it has an estimated depth of 40 to 100 miles. This was partly found by a couple of ways, but one was Hubble found it because it saw water venting into space, so that was one clue. And there was another clue because the gravity field of Europa changes as it's rotating, and it's felt that because of that change in gravity field, there must be water affecting the magnetic field around the planet. And so the magnetic field is affected as it rotates, and so the feeling is there must be something moving underneath, and it's guessed that was probably a salty ocean that's causing currents that are affecting the magnetic field. So to study this, there's going to be a mission. So there is planned to be, if it survives, a mission in the 20s called the Europa Clipper to go and study Europa in more detail, because with all this water, it's felt that there might be some signs of life in this buried ocean. Okay, this is Ganymede, which is the largest of the moons. It's 8% larger than the planet Mercury, but only 45% is massive, so it's not real dense. It's a metallic core, and it's the only moon that has a magnetic field of any of the moons in the solar system. And it's probably has a magnetic iron core, which is responsible. This was a picture of 182 composite images done by Galileo and Voyager to combine. This is a picture, this particular picture is all due, no, it's again, it's a composite, Galileo and Voyager, 100 meters per pixel resolution. And you can't make too much out of this, but if you look in this one red square, this is what it looks like. So there's a lot of detail on the surface here of it. And it's all looked to be fairly old. The estimate is that the dark areas are 4 billion plus years old and cover about a third. The lighter regions are cross-cut with a lot of these grooves that you can see here, thought to be almost as old, but maybe not quite as much. And this, the cause of this is not clear, but it's probably, again, tidal effects due to tidal heating, due to the passage through Jupiter's gravity. This is, again, another, they discovered, the feeling now is there's also an ocean underneath the surface of Ganymede, like we've been talking about with the first two moons. And so the feeling is that this ocean may actually contain more water than entirely exists on Earth. And it's interesting, because of the magnetic field, it has two aurora on both poles, and it's because of these aurora that they estimated how much water there is. And this is kind of cool. What it is because of this, the aurora is moving as the Ganymede is orbiting, and so they determine the motion of the aurora has to be due to the fact that the crust underneath, something underneath the surface is moving as it goes through the magnetic field. So through this motion of the aurora, they figured out this water exists. And so they estimate that it's 60 miles thick, 10 times deeper than the Earth's oceans, and is buried underneath a 95-mile crust. All this from the motion of the aurora that is observed. So, pretty amazing. Yeah, and another paper, just very recent paper, suggests that it's not quite as simple as that some of this is a combination of various forms of ice. Ice 1 is the ice we're familiar with. And there are various forms of ice that get denser under higher pressure, and these areas is a sandwich of ice and water sandwich. So anyway, there's a lot going on. This is the last one we're going to talk about. This is Callisto. It's just cram full of craters. It's quite old, very little activity. This is one of the craters that probably goes back to the early days of the formation of the, well, at some point during the early formation of the solar system, and just a picture taken by Galileo. This is one picture, this is the highest resolution picture of any Jupiter moon. It was taken on the surface of Callisto. These knobs are about 260 to 300 feet tall, and they're ejecta from one of these craters from some asteroid that hit the planet or the moon quite some time ago, probably billions of years ago. They're slowly eroding, but they still are there. And the smallest features in this image, which is pretty incredible, is 10 feet. Pretty amazing. And this was done by Galileo, this picture, in 2001. Okay, so that's all of, this, I may not get through Saturn, and if I don't get through Saturn, we'll pick it up at the luncheon meeting, but we'll see how far we get with Saturn. Okay, Saturn. So here's a wonderful picture that was taken by Cassini. As I said, there are 3,364 pictures taken by Cassini. So they're all there. That just happens to be one of them. You can see some of the moons. There's a couple moons. And this is actually the reference for this particular one. This is just a brief overview of Saturn. Its average distance is 9 Earth radii, or 9 Earth distances from the Sun instead of 5 for Jupiter. Rotation is pretty fast. It's a little over 10 hours. It has a significant tilt to its axis, though. It's 26 degrees, almost very similar to Earth's, so it has seasons. The temperature is about 50 degrees cooler than on the surface of Jupiter. It's minus 285, but it has a very hot core. Again, not as hot as Jupiter, but quite toasty. And you have all the moons and the rings and all. So this is talk a little bit about Cassini. Cassini was launched in 1997, and it made several passes around the inner solar system to gain some additional speed. Swung by Jupiter in 2000 and entered orbit in Saturn in 2004, July 1st. This is what it looks like. It is filled with instruments. It has remote sensing instruments, optical and microwave cameras, spectrometers, radio, and radar. It has fields to measure magnetic fields, mass, electric charges. It can also measure composition of particles and strengths of plasma. It also had another major mission, which was called the Huygens probe. This was made by the European Space Agency, and I'll talk about it, but it was designed, it's a lander. It actually landed on the surface of Saturn, of Titan. And we'll talk some more about that. Pretty big satellite. This is 22 feet high. Okay, so this is a cartoon that kind of shows what Cassini has done. You may know, or you maybe don't know, Cassini doesn't exist anymore. It was purposely flown into Saturn last year. But this starts in 2004, and 13 years, and it tracks what is done. And it has 294 orbits of the planet, 127 Titan flybys, 23 flybys of Enceladus, and some of the other satellites or moons, only 15. And what this does is this inner row of dots is the number of times it actually imaged Titan. And then the next row is how many times it imaged Enceladus right here. And then the other dots have to do with the other planets. So it's obviously focused on Titan and Enceladus, and you'll see why in a bit. This is a comparison of the two planets and their atmosphere. This is the one I showed earlier for Jupiter, and this is Saturn. And you'll notice that several things. The main difference is the elements are the same, the atmosphere elements are the same, but the atmosphere goes down much further. In columns. Instead of 150, it's goes down, and there's a lot more water, as it turns out, in the atmosphere. And so it consists mostly of molecular hydrogen, much like Jupiter. There are some differences. I'm not going to go into those. but the cloud layer is thicker. Weaker gravity, because of the weaker gravity, which is 2.5, well, which is much stronger, the atmosphere, Jupiter's atmosphere is pulled in much tighter. Saturn's atmosphere, because of the weaker gravity, is less, and so the atmosphere is spread out over a much greater thickness. Also, because the atmosphere is much thicker, there are fewer holes in it and fewer gaps, and so you don't see as much pretty detail in the surface of Saturn as you do on Jupiter. And you can see that from the pictures just already. Yeah, and this just shows a cartoon of the various layers. Molecular hydrogen on the outer edge, and then helium, and in both of them. Helium dissolves in the hydrogen in both planets. And the difference occurs in the inner part. Neon is a part of both planets, and the pressure in Jupiter, neon dissolves in the hydrogen, and that allows the hydrogen to actually react with the core and dissolve it. And so the core is etched away, and so there's likely to be no solid core in Jupiter. But in Saturn, the neon is, the pressure, the gravity is not as great. Neon is not dissolved, and it's intact. It's an inert element, and it's protecting the core. So it's thinking that Saturn has an iron core, or not an iron core, but a rocky core. This also compares the wind speeds. This is Jupiter again, and this is Saturn. And you'll notice that we're talking about 300, 400 kilometers an hour. And look at this. This is 1,500 kilometers an hour. Not clearly understood why. You'll notice also one of the other differences. It's all east to west to east, and just here's zero here. Very little motion in the east to west. Whereas in Jupiter, there are larger regions of east to west versus west to east. Okay. There's storms that occur on Saturn, and this is one I'll talk a little bit about that was seen by Cassini in December 2010, and it resulted in a huge increase in the surface temperature, 150 degrees warmer surface temperature than before. They also found an unexplained amount of ethylene that all of a sudden appeared. And anyway, I haven't talked much about where these pictures were taken from. This one was taken from 1.4 million kilometers and away from, I've missed the million what, but it's kilometers. This shows the storm February. That was in December of 2010. This is what it looked like in February of 25th of 2011. It's expanded, and this thing, what's happened is it eventually goes all the way around, and I'll show you that in a minute. But this storm occurs about once every 30 years, which happens to be the orbital period around the sun. It's Saturn's a year is 29 years. So once every 30 years, 29 years, this type of storm seems to happen. And it has to, remember, Saturn is inclined, so it has seasons. And so the northern winter is when this storm occurs, and it's a cooling of the atmosphere in the northern winter produces instability. And it only seems to happen once. It started in December, and it pretty much ended in August and later in 2011. But you can see its progression here, and you see it wraps around itself. This is probably the most clear image. And then now it's just kind of becomes a blur, and it's getting less distinct as August comes in. So this is also another interesting feature that later on in the Cassini, you'll see Cassini started out when it first came in 2004. It was looking at the southern end side of Saturn. As towards the end, is now looking at the north because the tilt changes as it goes around the sun. And so there's this hexagonal pattern on the top, and this is six-sided, by the way. And this is just a more detailed picture of this. It was first looked at by Voyager, and nothing has ever been seen. This is a very stable hexagonal pattern that, that exists in the polar area. And there's inside of it, there's a polar vortex that's whipping around. But this thing isn't changing. It's not moving. It rotates as the planet rotates, but it's fixed relative to the planet, whereas this vortex is spinning around inside. And it's really quite remarkable. There's nothing like it. Earth can't form a fixed pattern like this in its atmosphere because it has a surface. Saturn doesn't have a hard surface, so once something like this becomes in place, it tends to stay there. Now you might ask, well, how did it start? And there's only a lot of guesses about this, but there has been some modeling, and it's thought to be that there is some steep variation in the gradient in the speed with latitude as you go down into the planet, and that steep change in speed of rotation of the atmosphere down lower may cause this, and they've done some modeling here and shown that various shapes can actually form. And if you want to read about that, you have to go to a reference. But there are analysis that shows that, yeah, you can actually do this, and it has to do with the details of the rotation of the planet's atmosphere. Now, this is probably not going to work either. This is meant to show this how this inner part whips around and the outside part doesn't. And I probably, oh, here it is. Okay. All right. Yep, okay, I just did it once, and so I can do it again. See how the inner part is going around, but that hexagon on the outside is not moving. So why? Good, no one knows. But it's fixed. There are guesses. There's some understanding of it, but it has to do. It is possible in a surface that in a planet that does not have a hard surface that you can get patterns in the atmosphere that can cause this, and they modeled it and shown it. So now let's talk about Saturn's rings. These are probably visually the most interesting feature. You notice that there's not much texture to the surface, but the rings are just amazing. They extend quite a ways out from the planet, 7,000 to 80,000 kilometers. Thicknesses of 10 meters to as much as a kilometer, so they're not that thick. They're mostly water, water ice. Particles of 1 centimeter to 10 meters with enough mass to make a moon about 250 kilometers in size. Why do the rings exist? And there's two theories. One is they're left over from Saturn's origin, 4.6 billion years ago, the origin of our solar system. And the other is a collision with or a moon that came too close to the planet and got ripped apart by tidal forces. The fact that the rings are so highly reflective and the ice seems to be very clean suggests that they are younger than 4.6 billion years. So I think the thinking is that they're most likely due to an interaction with some kind of object that came by and got ripped apart. This is an interesting picture. This picture is taken backlit, so you can't ever see this from the Earth. The sun is over here, and we're looking through the rings with the sun coming through. And this outer ring, which you didn't see at all in these other pictures, only shows up clearly from this backlit view. And this is some of these planets. There's Earth, by the way, right there, a little dot. There's the G ring, which is what we weren't seeing before. These are all these inner rings, the outer one here being the A ring. This is called the E ring, and this is the planet Enceladus, which we'll talk about. The G ring is, this image by itself was 165 images taken by Cassini in 2006, put together. This G ring is created by stuff essentially we'll talk about that hopefully, that is coming from Enceladus. The Enceladus has volcanoes, and they're emitting cryovolcanoes, water type of volcanoes, and they're emitting this, and it's created this ring. Okay, this is just a comparison. This is a picture sun-lit, and this is backlit. It's just showing the comparison of the ring pattern. And all of this stuff is due to the water and salt that coming from the planet right there, Enceladus. This shows you the pattern of the rings, the innermost that goes almost right up to the surface of the planet, the D ring, which isn't very visible, the C ring, the B ring, the famous Cassini division, the A ring, and you'll know all these gaps are created by moons. They're embedded in those rings. Otherwise, it would probably be continuous. And in fact, the famous Cassini division is thought to be caused by the moon Mimas, which has a resonance with the particles in it. And so the particles go around twice to every rotation of Mimas, and they get a boost when Mimas is near, and they get kicked out of that gap. And so that's why that gap exists. And there's a similar story for these other gaps as well. The other question is, why are the rings so cohesive? Why don't they just dissipate? And again, a small moon plays a role in this. The Atlas moon is a tiny one out here. It actually orbits around the A ring, and it kicks out any particles that stray away, and it kicks them back in to the A ring. This is the rings. This is the full sweep of Saturn's rings, and this is the inner part. And I couldn't get it. I decided to cut it in half. But here's the first part of the B ring, and here's the last part, the Cassini. And here's the various gaps in much more detail. And this is even more detail. This is the highest resolution color image of any part of the Saturn rings. The inner part of this is about 60 some kilometers, miles from center. Again, water ice, but why the color is not completely known. And one of the interesting features of this is that the resolution on this picture is that the ringlets the narrowest ringlets here are 25 miles apart. So that's you look right in here. So the narrowest,